Hello, welcome to chapter 5, and today we're going to be talking about linear second order equations. So, what are these? Obviously, this is linear equations and second order. So these are going to be dealing with y double prime, alright, and then obviously, so they're gonna look like something like this. So we have p, or I'm just gonna call this a y double prime plus big P y prime plus big Q y equals big G. And then so I'm going to use a simplification, and so they're going to look like this, and I'm going to use this small p equals big P over A, small q equals big Q over A, and then small g equals big G over A, right? So we can simplify this equation as y double prime plus small p y prime plus q y equals small g. So this is what these equations look like. Now, likewise, if P and Q are continuous over some interval, then there exists a unique solution given initial conditions. So with initial conditions, when and not f, g is equal to 0. So the first thing I want to talk about is this concept of superposition. So this time we're going to have a few different ways to solving these problems, and one thing is if our equation has, so suppose it has two solutions, y of 1 and y of 2. Okay, these are solutions. Then our answer, then any solution to our ODE can be expressed as a linear combination of these ones. So y is equal to c1 times y1 plus c2 y2. This is called superposition. It can be either one or both of those these solutions. These are called, and so the set is called the set of fundamental solutions, y1, y2, and basically what we're saying is y is equal to the span of these solutions, right? If you were to think of this as like a vector space of all of our y's, right, of all of our functions, then the span of these, this is y1, this is y2, this span y is going to be somewhere in here. So obviously this, so basically this depends on the linear, on whether or not the this y1 y2, right, the span is linearly independent, right? So how can we determine things are linearly independent? Well, we can take, we check the determinant. Is the determinant non-zero, right? So this is called the Wronskian of our fundamental solution, and it's going to look y1 over y prime of 1, y2, y prime of 2, and then so we want to check what that is. So it's going to be y1, y prime of 2 minus y2, y prime of 1, right? And then we want to check is this equal to 0? And if it's equal to 0, then we have a linear independent set of solutions. So the Wronskian can be extracted to any arbitrary. So W of some y is going to be y1, y prime 1, y prime, y double prime 1, y n minus 1, and then all the way to y n, and then up to y n minus 1 prime of y n. Now there's a nice theorem called Abel's theorem that can help us here. And Abel's theorem essentially says that if P, Q are continuous over an interval AB, then the Wronskian of y1, y2 is equal to some constant times E times negative PT dt, which is either 0 everywhere or I'm gonna put this in big in green, or 0 nowhere. All right, that's nice. And so in the next bit, I'm gonna look into solving one of these situations where we have a single or a second order linear ordinary differential equation. There's a few different techniques we have for these type of problems. So see you then.